Welcome to this ninth online lecture session of the course Engineering Thermodynamics. In our previous lecture, we have started our discussion on the use of steam tables for obtaining the properties of water in its different states. Okay, so we have initially taken the practice of saturation liquid table. So we have found that for saturation states, we only need to uh, uh, have the knowledge of a single thermodynamic property in order to determine all other properties. Okay, so the idea was, if I just go to my PPT, so this is my presentation. In this PPT, I have actually already shown you the saturated water temperature table and saturated water pressure table. So now after that, I have already shown you that how to locate the different thermodynamic states once these are actually specified. Okay, so now what I will do, I will give you a few problems. So let me first take up the first problem statement. So it's nothing but we are having a given temperature as 73 degrees Celsius. So value of temperature is given as 73 degrees Celsius, and it is given in the question that state of our substance is nothing but saturated liquid. So for this saturated liquid state, if temperature is 70 degrees Celsius, we have to determine that what will be the corresponding enthalpy at this state. Okay. So if now I refer to the saturation table, and particularly if I go to saturation temperature table, I will be finding that we are not having any value of temperature equal to 73 degree. Okay. Rather, we are having the closest values as 70 degrees Celsius and 75 degrees Celsius. So 73 is nothing but lying in between 70 and 75. So ultimately what we need to do now, corresponding to 70, I will be noting the value of enthalpy, which is 293.07 kilojoule per kg. Then corresponding to 75, value of enthalpy is 314.03 kilojoule per kg, and we need to determine value of enthalpy. Now I suggest all of you to please apply the linear interpolation and try to find out the value of enthalpy H corresponding to 73 degrees Celsius. Okay. However, I will also try over here. So if I do it, it will be using the linear interpolation, it will be nothing but H minus 293.07 will be equal to 314.03 minus 293.07 divided by 75 minus 70 and whole multiplied by, I am writing in bracket, 73 minus 70. So if you solve this equation, ultimately you will be finding that H is nothing but equal to 305.646 kilojoule per kg. Okay. Now one more question let me give you. So what I am saying now, let us consider, it is given in the question that we are having temperature of 70 degrees Celsius. Okay. And it is given that corresponding to this 70 degrees Celsius, we are having given value of enthalpy as 1150 kilojoule per kg. Okay, so this is the value of enthalpy given, and temperature is given, and it is not specified in the question whether it's a saturated state or a subcooled state or a superheated state. Okay, so now over here what we have to do, we have to use our steam tables first in order to determine whether our state is actually superheated, saturated or subcooled, or it is in the liquid vapor mixture region. Okay, so for that what I will be doing, I will be now once again referring to my steam table, and corresponding to 70 degrees Celsius, if I see the value of HF, so corresponding to 70 degrees Celsius, the value of HF is nothing but equal to 2 93.07 kilojoule per kg, and if I see the value of Hg, so it is nothing but equal to, at the same temperature, Hg is nothing but equal to 26.1 kilojoule per kg. Okay, so the meaning is clear that at 70 degrees Celsius, which is the given temperature of the thermodynamic system, our enthalpy is also given as 1150. Okay, now corresponding to 70 degrees Celsius, our liquid enthalpy HF is 293 and gas enthalpy is nothing but 2626. So it means this 1150 is actually lying in between HF and Hg. So if any property is lying in between HF and Hg, it is nothing but in our which region? It is nothing but in our liquid plus vapor region. So if it is in liquid plus vapor region, then we can determine that how much fraction of vapor we are having. So how we can determine? We know that any property in between the liquid vapor domain is nothing but equal to HF plus X times HFG. Okay, so now I know the value of HF, I know the value of Hg, I can find out HFG as nothing but equal to Hg minus HF, or directly if you go to your steam table, you will be finding directly the value of HFG as a given parameter only, and this value of H, it is our given thermodynamic property which is 1150. So if you use this formulation, you can simply obtain the value of X. Okay, so you can easily determine value of X. All of you please mute your microphone. Okay, so we will be easily able to determine the value of X, which is our dryness fraction. Okay, now let us take one more situation. If I now say that my enthalpy is same 1150 kilojoule per kg, but now my temperature is nothing but equal to, so this is my enthalpy, and temperature is now nothing but equal to say 270 degrees Celsius. So if temperature is 270 degrees Celsius, we can clearly see that corresponding to 270 degrees Celsius, the value of HF is nothing but equal to, value of HF is nothing but equal to 1185.1 kilojoule per kg. Okay, so now what we are having, our given enthalpy is actually less in comparison to HF at the given temperature T. So that's why this state will be nothing but our subcooled, or I should call it as compressed state. Okay. So this state, whatever we are having, that will be nothing but either our subcooled state or compressed state. Okay. Then we have the another case. If I say consider that my temperature is 270 degrees Celsius only, but value of enthalpy is say 4500 kilojoule per kg. Okay, so now at this state, what will be happening? If you see corresponding to the temperature of 270 degrees Celsius, if you refer to your steam table, you will be finding that value of Hg is nothing but equal to 2789.7 kilojoule per kg. So it means your H, given H is nothing but greater than Hg at that particular temperature. So that's why what will be happening, I can simply say that my given state is nothing but a superheated state. Okay, so my given state is nothing but superheated or rarefied state. Okay, now let us try to subsequently go into more details of the table. So till now what we have done, we have only seen the use of saturated tables for determining the property and use of saturated table for determining or for specifying the given thermodynamic state of the system. Okay, so at this moment, with the help of saturated table, if two properties are given and physical state of the system is not specified, we are now easily able to determine that whether our state will be compressed or our state will be superheated. Okay, so this much we have already learned. But now at this given compressed or superheated state, how to determine the value of other properties, that let us try to see now. Okay, so let me first start with the superheated state. So already I have told you, for superheated state, if I show you the TV diagram, from the TV diagram you can clearly see that if I have any constant pressure line or if I have any temperature, so what will be happening? If my point is on the right hand side of saturation, vapor line, that particular region we call as nothing but our superheated region. Okay, and I have already told you that if we are having a substance in superheated state, we require two thermodynamic properties to specify the state. Okay, so how many properties are required? Minimum two thermodynamic properties are required to specify the state. Okay, so there is a requirement of minimum two thermodynamic properties. So now what I will be doing, let me show you the tables, superheated tables with the help of slides. So in this my slide number 5, you can see that we have superheated water. So tables for the superheated water. So you can clearly see on the left hand side we have temperature column. Okay, so on the left hand side we have a table which shows the temperature values. We have a column which shows the temperature values. Then next point is nothing but specific volume. Next point is internal energy. Next is enthalpy. Next is entropy. Okay, and these tables are actually separately available for different values of pressure. Okay, so for example, here you can see my range of temperature I have included from 50 to 1300, and now this first entry, whatever V, U, H, S are there, these are corresponding to a pressure of 0.01 megapascals. Okay, so this is very important point. Like first entry, whatever I have specified, you can see over here, this first entry is corresponding to pressure of 0.01 megapascals. Okay, and corresponding to this pressure in star, we are having one temperature mentioned, 45.81 degrees Celsius. Okay, so it means this 45.81 degrees Celsius is nothing but saturation temperature corresponding to this pressure. Okay, so what is it? Let me specify. So as I have told you that I have some constant pressure line P1 over here. So now while this constant pressure line P1 will be crossing the saturated vapor and saturated liquid line, corresponding to that it will be having certain value of temperature. Okay, so this temperature is nothing but saturation temperature corresponding to pressure P1. Now if I take some another pressure line, say P2, so you can see that this P2 pressure line is crossing our saturation liquid and saturation vapor curve at some different value of temperature. So that's why this now new value of T set, whatever I am getting, this is actually corresponding to pressure P2. So it means each pressure has unique value of saturation temperature. Okay, so now let me once again go to the tables. So in table you can see that first I have written pressure as 0.01 megapascals and corresponding to this pressure we have 45.81 degrees Celsius is given. So this 45.81 degrees Celsius is nothing but it represents the saturation temperature corresponding to pressure of 0.01 megapascals. Okay, and you can clearly see while we have the entries of temperature in our extreme left column, the entries of temperature are starting from 50 to 1300, and before that we have the very first entry which is written saturation and star. Okay, so it means the first entry of every pressure table represents the saturation state corresponding to it. Okay, and moreover, we know that in saturation we have two states, liquid and vapor. So this particularly represents the saturation vapor state. Okay, so the very first entry which is written saturation with star. So star means whatever the temperature is mentioned corresponding to pressure, that is the value of temperature to the first entry. Okay, and the properties, specific volume, internal energy, enthalpy and entropy are mentioned corresponding to the saturated vapor state. Okay, and then we have the other entries. Now if you see the pressure table corresponding to 0.05 megapascal, so corresponding to 0.05 megapascal, our saturation temperature is 81.32. Okay, so that's why corresponding to the saturation value is given, and then corresponding to temperature of 50 degrees Celsius nothing is given. Why? Because if the saturation temperature is 81.32, because of that what will be happening, 50 degrees Celsius corresponding to pressure 0.05 megapascals will not be a superheated state. Okay, so that's why we don't have superheated properties available at this situation. Similarly, you can see the pressure I have represented next one as 0.1 megapascal, corresponding to which our saturation temperature is 99.61. Okay, so this is like about our superheated tables. Now if you refer to page number 920, 921, 922 and 923 of your steam tables which I have uploaded on Moodle, you can see that we are having detailed superheated tables given for wide range of pressure conditions. Okay, so whatever the tables I have uploaded, you can refer to from page number 920 to page number 923. Okay, so we are having wide range of pressure conditions corresponding to these pressure conditions. Superheated tables are specified. Okay, now let me take up some questions in order to learn the use of superheated tables for locating the value of property. Okay, so what I am doing, I am giving you a thermodynamic state. Let me consider the pressure is 1.2 megapascals, and let us consider temperature given is nothing but 250 degrees Celsius. Now what you have to do, corresponding to this pressure and temperature, you have to determine all other properties, specific volume, internal energy, enthalpy and entropy. So what you all can do, all of you please use your respective steam tables whatever you are having and try to identify the value of these properties by locating your thermodynamic state. Okay, using the appropriate table. So this state I am already specifying that it is nothing but a superheated state. So whatever the answers you are getting, you can write in the chat box and you can then compare with others. In the meantime, I will also locate the thermodynamic property, thermodynamic state in the superheated table. I also have steam tables and I'll give you the correct answers over here. Okay, I'll write the correct answers on the board. So those who are not able to see, what you have to do, now all of you please go to superheated table. So if you go to page number 921, on the page number 921, we are having this temperature value which is changing from 200 to 1300 degrees Celsius, and corresponding to that I have fixed pressure entries. So the first pressure entry is for 1 megapascal, second pressure entry is for 1.2 megapascal, third pressure entry is for 1.4 megapascal. So which one I want? I want nothing but 1.2 megapascals. So I think on page number 921, if you go, you will be able to locate the pressure condition of 1.2 megapascals. Okay. And now on this page itself, if you go to the value of 250 degrees Celsius temperature. So if you now choose a row which is having temperature of 250 degrees Celsius, by locating that particular row of 250 degrees Celsius and looking into the table for pressure of 1.2 megapascals, you will be finding that value of specific volume is nothing but equal to 0.16326 meter cube per kg. Okay, and if you find out the value of corresponding internal energy, that is nothing but equal to 2612.9 kilojoule per kg. Okay, if you find out the value of enthalpy H, that is nothing but equal to 2816.1 kilojoule per kg. And if you look at the value of, yes please.
Sir, you are writing
Sir, you are
200
writing
degrees
200
Celsius.
Sir, it is of 200 degrees Celsius.
200 degrees Celsius.
Oh, sorry, I have made a mistake. Let me correct it. Okay, so now I am correcting the values. So the correct values are 19241. Sorry, so I have written the incorrect values corresponding to 200. So if I go to 250 degree Celsius corresponding to 250 degrees Celsius, yes, you all are correct. Specific volume is 0.19241 meter cube per kg. If you write the value of internal energy, it is 2704.7 kilojoule per kg. If you write the value of enthalpy, it is 2935.6 kilojoule per kg. And if you see the corresponding value of entropy, it is nothing but 6.8313 kilojoule per kg. Okay, so I think you all are now able to correctly locate the values from our steam tables, particularly for superheated state also. Okay, now let us slightly complicate our problem, and now what I will do, I will give you some problem where you will not be exactly able to locate the parameter, rather you have to employ some interpolation steps. Okay, so what I am saying, let us consider a thermodynamic state where pressure is equal to 0.8 megapascals. Pressure is nothing but equal to 0.8 megapascals and temperature is 815 degrees Celsius. Okay. So now can you determine the value of let us determine the value of internal energy, because if you are able to locate one, you will be able to determine others also. Okay, so let me take up only the property of internal energy. So all of you please practice and try to identify the value of internal energy for temperature of 815 degrees Celsius if our pressure is 0.8 megapascals. Okay, so I am specifying you that it's nothing but a superheated state, so use the superheated steam tables. Okay, so now let me once again look into the steam tables. So if you go to page number 920, on page number 920 we have this pressure value of 0.8 megapascals given, and now if you see the corresponding range of temperature values, you will be finding that we are having spacing of 100. So we have a reading corresponding to 800 degrees Celsius, and we have another reading corresponding to 900 degrees Celsius. However, we want to determine value at nothing but 815 degree Celsius. So how to do? So what I will be doing, I will be first writing the value of internal energy from our table corresponding to 800. So if I write corresponding to 800, I am getting value of 3662.5 kilojoule per kg. Okay, so that is what I have got corresponding to 800, and corresponding to 900 I have got the value as my 3854.5 kilojoule per kg. Now you have to determine this particular value corresponding to temperature of 815 degrees Celsius. So nothing but we have to employ linear interpolation. So now I will not write the detailed equation, rather I'll give you the final value. Okay, so if you apply linear interpolation, finally you will be finding your internal energy corresponding to 815 degrees Celsius and pressure of 0.8 megapascal. Nothing but
3691.5.
yes, correct. It is 3691.3 kilojoule per kg
Yes.
if you are going to be precise. Okay, so it's 0.3 instead of 0.5. Okay, so this is how we can determine. Now let me slightly more complicate the problem. Now what I will do, I will give you a situation where pressure is also not known, is also not given in the table, and temperature is also not given. Okay, so let me write up the condition of, let me write the pressure of, condition of pressure as 0.9 megapascals, and condition of temperature, say my P is 0.9 megapascal, and say temperature is 815 degree Celsius. Now how to determine the value of internal energy for this particular combination? Okay, so that is our question.
We can take average of 0.8 and 0.1, 1.0 megapascal.
Yes,
The
so
average of pressure at 1 megapascal and 0.8.
yes, so what we have to do over here, first what we will be doing, first we will be finding the properties corresponding to 0.8, because if you see 0.8 and 1 megapascal are the entries available in our tables. Okay, so that's why what I will do, first I will calculate the values of all the properties corresponding to 0.8 megapascals and then corresponding to 1 megapascal. Okay, so for example, if you see corresponding to 0.8 megapascals, just now we have calculated. Okay, so for 0.8 megapascals, just now we have calculated by using interpolation that corresponding to 815, our value is nothing but 3691.3 kilojoule per kg. Now if I go to 1 megapascal, corresponding to 1 megapascal at 800 degrees Celsius, 900 and 815 I have to determine. Okay, so at 800 you can refer to the table, value is 3661.7 kilojoule per kg. For 900 it is 3853.9 kilojoule per kg, and this is what you have to find out. So if you calculate this,
3690.53.
yes, 3690.53, exactly correct, kilojoule per kg. Now what we have to do, now you can clearly see that the temperature of 815 is already catered in both the situations. Okay, so now I can write the next situation that my temperature at temperature of 815 degrees Celsius for pressure of 0.8 megapascals. Value of my internal energy is nothing but equal to 3691.3 kilojoule per kg. For pressure of 1.0 megapascals, this value just now we have calculated, it is nothing but 3690.53 kilojoule per kg. Now we require this to be calculated.
Sir, is it 3690.915?
It is 3690.8. Okay. So if you calculate, to be precise, it is 3690.8. Okay. So it means this is nothing but a slightly complicated case where we have to do interpolation 2 times. Okay. So I believe if you all are able to determine properties for this particular combination, for this particular situation, whatever I have taken, you will be easily able to determine the value of properties for superheated state. Okay. Now what I will do, let me now take up another situation.
Sir,
Yes, please.
sir, here we take average after interpolation 2 times.
So second time you can take average also. Why average? Because your 0.9 pressure is immediately is actually the average of the 0.8 and 1. Okay. If it is other than 0.9, in that case you have to use interpolation. You cannot directly take average then. Okay.
Okay, sir.
Now let us take another stage where we are having compressed, or I can also call it as nothing but subcooled state. Okay. So for compressed or subcooled state, what we have to do, once again for this particular state, if I just show it on a TV diagram, so any thermodynamic state which is on the left of the saturation liquid line, that we call as our compressed state. Okay. And for compressed state also we require 2 thermodynamic properties to specify the state. So we require 2 thermodynamic properties. For this also, how many? We require 2 thermodynamic properties. So it means that the tables of compressed state are nothing but exactly identical to that of the tables of superheated state. Okay. So let me just show you the table for compressed state. So you can clearly see for compressed liquid state, tables are exactly identical to that of the tables as we were having for superheated state. So you can see over here we are having pressure of 5 megapascals, and corresponding to 5 megapascal saturation temperature is 263.94 degrees Celsius. So that's why any entry beyond 263 is actually not included over here, because as the temperature will be reaching to 263, state will become saturated liquid. So beyond that it will go to actually superheated region. So that's why in compressed table we don't have entries beyond 263 in our tables. Okay. So I have also shown here table for 10 megapascal and a table for 15 megapascal. Okay. Now I think we need not to do much practice of compressed tables, because the way you have used superheated state tables, in the similar way we have to use the compressed state tables. Okay. Only one thing I would like to show you. So if you go to page number 924, whatever I have given, on the page number 924, all the compressed tables are given, and the range of pressure is taken as 5 megapascals, 10 megapascals, 15, 20, 30 and 50 megapascals. Okay. Now one important point I would like to tell you all, particularly in terms of the compressed liquid state, that many of the times we will be finding a situation either in your exams or particularly when you go for the competitive exams also, you will be finding that many of the times compressed tables are not available. Okay, so compressed or subcooled tables, subcooled property tables are not provided. So many of the times you will be finding a situation where question will be coming from compressed state, but compressed or subcooled property tables will not be provided. Okay, so this happens many of the times. So how to take up the situation under that scenario, that let us try to see. Okay, so now if you go to your saturation table, if you go to your saturation table, you will be able to find out. For example, if I take up the case, so what I am doing, I am now taking up a case of 5 megapascals. Okay, so for compressed state, I am referring to pressure of 5 megapascals, and let me refer to temperature of 100 degrees Celsius. So if I take a situation where I have pressure of 5 megapascals and temperature of 100 degrees Celsius. Now for this particular situation, if I refer to compressed state table on page number 25, 924, on page number 924, I will be finding that value of specific volume is nothing but equal to 0.0010410, okay, meter cube per kg. If you refer to value of internal energy U, so value of internal energy U is nothing but equal to 417.65 kilojoule per kg. If you refer to value of enthalpy H, you will be finding H is nothing but equal to 422.85 kilojoule per kg. Okay, and if you refer to value of entropy S, you will be finding S is nothing but equal to 1.3034 kilojoule per kg Kelvin. Okay, so these are nothing but the properties corresponding to 5 megapascal and 100 degrees Celsius. Now what I am asking you to do, that you simply go to the saturation temperature table. Now all of you please go to saturation temperature table, and corresponding to temperature of 100 degrees Celsius, write down the corresponding properties for saturated liquid state. Okay, so write down the corresponding properties for saturated liquid state. Now if you refer to the saturation temperature table, and if you go to 100 degrees Celsius, if you write down the value of specific volume of liquid, it is nothing but equal to 0.001043 meter cube per kg. If you write down the value of internal energy of liquid, it is nothing but 419.06 kilojoule per kg. If you refer to the enthalpy, it is nothing but equal to, if you refer to enthalpy, it is nothing but equal to 419.17 kilojoule per kg, and if you refer to entropy of liquid, it is nothing but 1.30 kilojoule per kg Kelvin. Okay, so now yes, what I want to show that if you see the specific volume value, the change of specific volume upon increase of pressure, if you see corresponding to 100 degrees Celsius, our pressure is 101 kilopascal. So it means 101 kilopascal is nothing but our 0.1 megapascal. Okay. So at this pressure, if we see at this particular temperature, if we see pressure corresponding to saturated state, it is nothing but close to 0.1 megapascals. And now what is happening when we have gone to the compressed state, then in case of compressed state, though our pressure is now equal to 5 megapascals, all of you please keep your microphone muted. Okay, so though our pressure has increased from 0.1 megapascals to 5 megapascals, but the specific volume has almost remained same in both the situations. Okay, so you can see upon very high increase of pressure also, specific volume is almost same. So it means nothing but this is a liquid, so liquid is an incompressible substance. So even upon large change of pressure, we are having almost same value of the specific volume. Okay. Similarly, if you see in terms of internal energy also, the change is not significant. So this is also very closely approximated. And if we talk about enthalpy, then obviously we have slightly significant change. Why? Because enthalpy is something which includes in our definition H equal to U plus PV. Okay. So though U and V are not changing significantly, but our value of pressure has changed significantly. So if pressure is changing significantly, it will try to change the value of enthalpy by large margin. Okay, so that's why enthalpy is something which we cannot approximate corresponding to saturated state. However, if you see in terms of entropy also, we don't have much change while we are going to the compressed state. Okay. So from this particular illustration, we can conclude that if we are having compressed state given, if compressed or subcooled state is given and property tables are not available. Okay. So what we can do, we can simply refer to the saturated liquid state. We can refer to saturated liquid state column, and this saturated liquid state column we have to refer from temperature table. Okay, because in case of compressed state, effect of pressure is not prominent on some of the parameters. So that's why we will be referring to the temperature table. So whatever the condition is given, for example, if I take earlier case, pressure equal to 5 megapascal and temperature equal to 100 degrees Celsius, I need not to worry about pressure. I have to simply go to my saturation liquid state table, and from the saturation liquid state table corresponding to given temperature of say 100 degrees Celsius, I have to note down the values of specific volume V, internal energy U. So this I have to take corresponding to liquid state. So that's why I am writing VF, UF and SF. So these three properties I can easily locate. Okay. Now how to find out enthalpy? For enthalpy, what we will be doing, we will be finding that enthalpy of compressed state is nothing but equal to enthalpy F at 100 degrees Celsius plus our given pressure minus pressure at 100 degree Celsius times specific volume at 100 degrees Celsius. So if we just use this equation, by using this equation actually we can determine the corresponding increase of enthalpy from this particular saturated state to the state of high pressure. Okay, so this term over here nothing but will include the effect of pressure. So you can clearly see corresponding to HF of 100 degrees Celsius, we are having magnitude as 419.17 plus we have pressure of 5 megapascals. So 5 megapascal in terms of kilopascal I can write as 500. Okay, so 5 megapascal I can write as nothing but 500 minus pressure corresponding to 100 degrees Celsius is nothing but my 101.42 multiplied by Vf. So if I just do this calculation, I'll be able to determine the value of enthalpy corresponding to my compressed state. Okay, so this is one method, and another method could be that we will be simply writing.
So 5,001.
Oh, sorry, I made a mistake. Yeah, it will be 5,000. Sorry. Thanks for correcting it. Next, another thing I can write H compressed. I can also write as UF corresponding to 100 degrees Celsius plus value of pressure whatever we are having. So that value of pressure multiplied by Vf at 100 degree Celsius. So this value of pressure will be nothing but our 5 megapascals. So these two are the different modes which can be employed for obtaining the value of enthalpy at compressed state if compressed tables are not given. And why we are taking the value of specific volume, internal energy and entropy as identical to that of the given temperature at saturated liquid that I have just demonstrated in the previous slide. Okay. So what I will do probably with all this, I will conclude our discussion on the use of steam tables. So use of steam table is very important, particularly for the subject of thermodynamics, and many times we need to many times while we will be solving the numerical problems, we will be having requirement of locating the thermodynamic state and finding out the thermodynamic properties. Okay, so that's why you all please do practice few more problems in order to learn the proper use of steam tables. Okay, now one important point I would like to highlight, that we have one very general diagram which is referred to as Mollier diagram. So Mollier diagram is nothing but it is a graph in between H versus S. Okay, so a graph in between enthalpy and entropy is something which is referred to as a Mollier diagram, and on our Mollier diagram liquid vapor dome looks something like this. Now on this Mollier diagram we can have different constant pressure, constant temperature and constant specific volume lines. However, we will try to take up discussion on Mollier diagram after we are actually physically understanding the significance of entropy and enthalpy in our subsequent lectures. So that's why I will not discuss Mollier diagram at the moment, but whatever the properties we are having in terms of tables, so the graphical representation of all the tables on HS diagram is particularly referred to as Mollier diagram. So instead of using the table, if we are having Mollier diagram, that also we can employ for determining the value of different properties. But at the moment, I will not discuss about Mollier diagram. We will try to take it up after the understanding of enthalpy and entropy. So now I will stop at this point and we will have further discussion in our next lecture.